Alright, so the title of the talk is about solar cells. So I want to start with some nice pictures of solar cells that you see out there. Typical solar panels. Now, most of the solar panels and solar cells that you see out there on the rooftops or connected to the boards, different places, are based on solid-state semiconductor technologies. Basically, what makes a solar cell, a typical solar cell, is a p-n junction, similar to what you have in a semiconductor diode in an electronic circuit. And when we have n-type semiconductor next to a p-type semiconductor, n-type means you have a high concentration of electrons, p-type means a high concentration of holes. So electrons will diffuse from the n side to the p side, and some holes will diffuse from the p side to the n side, and what will be left behind is net charges, and these are stationary charges left at the border between the two. So you're going to have an electrostatic field between the n and p, and so when you expose this combination to light, optically, electron-hole pairs gives you free electrons and holes, and in this junction, the electrons will be absorbed to the positively charged side, which is the n side, and the holes will be repelled towards the p side, and this way you can get a current out of it. So that's the basic operation of a solid-state solar cell. Now, the type of solar cell that you may not be as familiar with is photo-electro-chemical solar cells. Here's an example. You can have a semiconductor electrode inside an electrolyte, and just similar to a p-n junction where you have a Fermi level difference between the p side and the n side and gives you this internal built-in electrostatic field, you can get that between the semiconductor and the electrolyte. In this example, this is one of the typical applications for photo-electrochemical cells, is to decompose water. Of course, you need to have a high bandgap semiconductor to be able to decompose water, because you need 1.2 volts at least to be able to decompose water and generate hydrogen. So again, this is the principle of operation is very similar to solid-state photocells. What you have is your semiconductor, which has a certain Fermi level, and then you have your electrolyte, and you can define a Fermi level for the electrolyte. And if there's a difference between them, you get a bending of the band gap for the semiconductor, and you can have accumulation of charges and electrostatic field on the surface of the semiconductor. What's the advantage of these type of cells? Well, it's really easy to make them. You don't need to have high temperature processes and doping. All you have to do is to take a sheet of semiconductor, dip it inside the right type of electrolyte. So we tried to make a PEC, or photo-electrochemical cell, using silicon. The problem with silicon is it doesn't give you enough voltage to be able to decompose water. That's what people are usually most interested in. If you can generate hydrogen from light, that would be awesome. But we tried to focus on other things. We tried silicon along with different types of solutions. One of the things that turned out to be working pretty well is a zinc solution. So what we have in this setup is basically a zinc electrode, which is dipped inside a solution of zinc chloride. And then we have the silicon electrode, which is the photo-cathode in this case. We are using p-type silicon, and the reason is that we want to, well, I'm going to get to that later on. So we have a p-type silicon next to the zinc electrolyte and the zinc electrode. Here's a picture of the real thing. We could get efficiencies up to about 4.5%. It's not a record high, but again, given the simplicity of the system, it's pretty good. Here's a little bit of detail of what happens. Here you have the band gap of silicon. It's p-type silicon, so the Fermi level is down there. And then the electrolyte, the zinc electrolyte, if you can convert the potential, the redox potential of the solution into its Fermi level. And basically for zinc, it happens to be up there. So the zinc electrolyte acts as n-type with respect to the p-type silicon. So what happens is when you put these two next to each other, you're going to have a depletion region and an accumulation of negative charges on the silicon surface, and you have accumulation of positive charges on the surface of silicon on the electrolyte side, which means that you have zinc ions next to the surface that show as positive charges here. And inside here you have a region of the p-type silicon which is depleted of holes. You have a depletion region. And if this is exposed to light, the generated electrons will be pushed by this electrostatic field towards the solution. In the solution you have zinc, positive zinc ions, and you're pushing electrons towards them. So what happens is your zinc ions will turn into metallic zinc, and they get deposited on the surface of the silicon. What happens on the other side, on the anode side, you have the zinc electrode, which is being consumed. Basically, the electrons that are pushed towards the solution by the semiconductor come from the zinc electrode on the other side. So what's happening in this cell is you are not really consuming zinc. You are oxidizing zinc on this side, so metallic zinc turns into ionic zinc on the zinc electrode side. And on the silicon side, you are turning zinc ions into metallic zinc. And as a result, you get a flow of electrons that's your generated electricity. Now, even though we are not consuming zinc in this process, the problem is that your zinc electrode will eventually be completely gone, right? Because you are taking zinc out of the electrode, depositing it on the silicon surface. You are recovering the zinc, but the zinc is not on the electrode side anymore. So one of the improvements we did in the next step was we added this copper electrode. We put the copper electrode on the bottom of the container that has a solution in it, and we use zinc powder instead of a zinc electrode. Now what happens here is the zinc powder gets consumed instead of the zinc sheet that we had before, and it gets deposited on the silicon surface. Here you can see a lot of zinc, and it's deposited on the silicon surface as very porous, very soft kind of material. And after it becomes really thick, it starts to peel off automatically and go back down to the surface. So this way you can have a full cycle for the process to keep going on. The zinc from here goes on top of the electrode and then falls back down. So this is some of the previous work we did for this type of cells. In this work, we decided to make a micro-scale version of this. See if we can make a micro-scale version which is packaged and nice instead of having this big container of the solution. So here's the schematic. Here's the idea. We basically wanted to have a silicon container, a cavity inside a silicon wafer, and fill it up with the zinc chloride electrolyte. And this bottom layer is the zinc electrode. So again, the same kind of process happens as before. We get zinc out of the zinc electrode, and it gets deposited on the silicon surface. The difference between this and the previous work was in here, the side of silicon that is being exposed to light, we're shining light from here, that's the surface where the reaction is happening. In this case, the source light is outside the cavity, but the reaction is happening inside the cavity. So the trick is you have to make this membrane thin enough so that light can actually penetrate inside. If you don't get light inside, there's no reaction going on, so you get no current from the cell. On the other hand, you don't want to make it too thin, because if the membrane is too thin, most of the light will just pass through without getting absorbed. So there's like an optimal thickness for that membrane that you have to be able to maintain. Now the fabrication process, extremely simple, just one lithography step. Open some openings, open up some open areas on a silicon wafer. We use the double polished silicon wafer. The reason we use double polish was we want to have a smooth surface so that when we thin it down, we don't end up having holes in it before we can get to a thin enough thickness. At the same time, the etching can be used to thin down the boundaries between different chips, and so it will be easy in the end to break them off. Here's an example of one of the fabricated devices. We used wet etching of silicon, the basic process most of you are probably familiar with, just using KOH to etch silicon, and we get the typical 54.7 degree sidewalls. Here's the size compared to a penny. This is a 2 by 2.5 by 2.5 or 3 by 3 millimeter opening, which ends up being about 2.5 millimeters on the bottom side. And here you can see the picture of a fully assembled cell. So we just took that piece of silicon, filled it up with some zinc chloride solution, and then sealed it with a sheet of zinc using some regular glue. You can see where the cavity is. This area, which is kind of bumped up, is where the cavity is. The solution is inside, and we used wire bonds to get the current out. And here's a test setup, just a light that we have characterized and made sure its intensity is about 1 sun. And finally, here's the IV curve that we could get for this device. Maximum current of about 15 or 150 microamps, and open circuit voltage of 0.35, maximum power of 27 microwatts for an area of 5.2 millimeters squared. If we do the calculation for the efficiency, it ends up being about 0.5%. It's not that high. It's not even close to the highest that people can get. But again, given the simplicity and low cost that you can build these devices for, might make it justified for some of the applications. So to wrap up the talk, we have demonstrated a miniaturized, microfabricated silicon-zinc photo-electro-chemical cell. The efficiency was measured to be 0.5%. You can still probably improve the efficiency by getting the best thickness for the membrane, and the future work would focus on long-term characterization and improvement of the cell. And I'm happy to answer any questions. Yes. We tried a lot of different things, and the only thing that